Welcome back, everybody. This is going to be my final of two parts in my lecture series on solving exponential and logarithmic equations. In this video, we're going to tackle logarithmic equations. Let's get started. A logarithmic equation is just simply any equation involving a logarithm, like this one, to solve log base 4 of x plus 5 equals 3 for x. And these involve a trick called exponentiation, which is objectively too long of a word. Exponentiation. Now, we already talked about in the third part of the previous lecture series that exponents, or exponentials, and logarithms are inverses of each other. They also serve as inverse operations. Just like how when maybe you have a 3x or a 3 times x and you want to isolate x, you would divide by 3 to undo that process. Here, I've got a logarithm preventing me from isolating my variable, so I'm going to use an exponential to undo it. Here, I have log base 4. So the way I exponentiate both sides, or the way I get rid of that logarithm, is by using my theorem from the previous video in reverse. If these two guys are equal, then I should be able to raise them as powers of the same base and still have a true statement. Here's what I mean by that. 4 to the power log base 4 of x plus 5 is equal to 4 to the 3. Now, we need to pause for a minute to discuss one last property of logarithms. And that is, if I have b to the log base b of x plus 5, or of anything really, let's just say of x, this is just equal to x. They cancel each other out. Remember that log base b of x is the inverse function to b to the x. So when I plug in f of f inverse of x, I just get back x. Let's put this maybe in a more particular context, though. Here, remember log base 4 of x plus 5 is the power I need to give 4 to get back x plus 5. So here's what the left-hand side of my equation reads as. 4 to the power that makes it x plus 5 equals 4 to the third. So if I have 4 raised to the power that makes it x plus 5, that just gives me back x plus 5 on the left-hand side. In other words, when I have a base to the power log of that base, they cancel. And I'm just left with the thing inside the logarithm. If you're taking away anything from this long conversation, it's that b to the log base b cancels out, and I'm just left with x. On the right-hand side, I will get 64. So that tells me x equals 59 is the solution to this equation. Let's try another one. Here, I've got substantially more work to do. There is a very big warning that comes with this problem. Only exponentiate. You should only exponentiate when there is one logarithm per side of the equation. But here you'll notice I have 3 logarithms on the left-hand side. So the first step is going to be to condense all of these guys into a single logarithm. How would I do that? Remember back to before we had our product and quotient rule that log of mn is log of m plus log of n? Well, in the problems we did in that section, it was more simple to write the product as the sum. But in this case, I actually want to write fewer logarithms, so I want to use this property in reverse. Notice that I have a sum of two logarithms here. So I can actually rewrite those two guys as log base 2 of x minus 3 times x minus log base 2 of x plus 2 equals 2. Similarly, from before, I know that when I have a quotient, I can split that up using subtraction. But here, notice I want to go in reverse because I have a subtraction that I want to write as a single logarithm. So I'm going to condense it all as division. X times x minus 3 over x plus 2 equals 2. Now that I have a single logarithm on both sides, I can exponentiate. So I'm going to write this as 2 to the log base 2 of my big, ugly, nasty fraction equals 2 to the 2. On the left-hand side, my 2 and log base 2 cancel, and I'm just left with x times x minus 3 all over x plus 2. On the right-hand side, 2 squared is 4. Why don't you pause the video here to see if you can finish solving this problem? Hopefully you were able to arrive that x should be 8 or negative 1. Again, this was just by multiplying x plus 2 over to the other side. That left me with a quadratic equation to solve. But there is a problem here. Let's go back up to the original equation. Notice that I can't actually have negative 1 as a solution because I cannot pass negative numbers into a logarithm, right? So this, by the way, does present a new domain issue to look out for. Is that if I have any logarithm showing up in my function, that input has to be greater than 0. Has to be non-negative. Or excuse me, it has to be strictly positive. So it cannot be negative 1. Negative 1 is what we call an extraneous solution. X equals 8, on the other hand, is still good to go. In this video, we saw how to solve logarithmic equations. That's going to wrap it up for this video and this series. I'll catch y'all in the next one.